Swayam Prabha. Digital India. Educated India.
So this is the ideal ranking cycle that we had introduced in the previous class. So this is the TS diagram, and we said that there are two pressure lines or levels over which the cycle is being completed. One is this pressure, which is the higher pressure, and this is the lower pressure. And we go from 1 to 2 to 3 to 4 and then back to 1. And from 1 to 2, there is pump, which is involved, or pumping work, which is involved, which increases my pressure from the lower pressure to the higher pressure level. And then from 2 to 3, there is heat addition. And then that's where the burning of the fuel, etc., happens. And the heat which is produced by the fuel burning is added to the thermodynamic cycle, fluid of the undergoing the thermodynamic cycle, water in this case, because we are looking at the steam tables. Now, from 3 to 4, there is an reversible or an asymptotic expansion that is happening. Of course, this is an idealization, and this is essentially we take it to a turbine, and the high temperature, high pressure steam that you have at 3 or at state 3 is capable of doing a lot of work for you, and this is exploited to run a turbine. And at the exit of the turbine, the steam is at state 4. And of course, this is saturated steam at 3, and 4 is a mixture of steam, vapor plus liquid. And then there is heat rejection, which happens from 4 to 1. This is you take it to a condenser and you reject heat. And then you basically complete the cycle. This is how the entire cycle gets completed. And of course, 3 to 4 is our leg, which is the most important one, because this is the one which is producing work for us. And we said that we can trace these points starting from point 1. This is at lower pressure P1. You know pressure, and you know that this is quality 0. Then knowing S1, you can find out S2. And this is at the higher pressure P2 and entropy equal to S2. And then you go to 3, which is at the pressure level P2, and quality is 1. And then this point is going to have same entropy, S3 is equal to S4. And this is S4, you know now, and you know P1. So you can locate this point. So you can see that knowing the two properties, again, we are going ahead and we're able to get to all these points. So then we were comparing our Rankine cycle with the Carnot cycle. We said that this is how we are going to view things without trying to do an exact computation, of course, which is possible, very much possible, but of course that is much more time consuming. So if you view our efficiency in terms of average temperature at which heat is supplied and the average temperature at which heat is rejected, then we can, by if one changes, the other changes, we can see, we can sort of get a feeling of how the efficiency would change. So our Carnot cycle is I mean, if we were to compare this Rankine cycle versus a Carnot cycle, then inside this we can draw a Carnot cycle by going this to this point 1 prime, not all the way to 1, and then having an adiabatic or an asymptotic, rather I should say an asymptotic compression, so that my pressure increases from P1 to P2. So you can see very clearly that in this case now, in the Carnot cycle, the heat addition is only happening in this leg, whereas for a Rankine cycle, the heat addition is happening over all these legs, and therefore the average temperature, this is the vertical axis, is the temperature axis. So you can see that there will be a much lower average temperature for the case of a Rankine cycle. And because the heat addition is now happening at a lower temperature, 1 minus QL upon QH is now lower, and therefore this this efficiency will be lower now. as compared to Carnot cycle. So why choose the Rankine cycle at all and not just work with the Carnot cycle as the ideal cycle? We said that there are two reasons, because when you're trying to compress things from 1' to 2' along this red dotted line here, you see that you are compressing a mixture of vapor plus liquid, and therefore this is not very easy to do. Okay, somebody asked me whether, I mean, here we are also having, so here we were saying that the liquid is what can cause difficulty. So somebody asked me a very logical question as to, if we are compressing here, then then how can we do that? And is that good enough? So the answer is that we can compress a single phase vapor or a single phase liquid. That is easy, or when we are working with them, then it is easier to do. Whereas when you have two phases, both of the mixtures, or as a mixture, that means that both liquid and vapor appearing together, then the difficulty arises, because one would get compressed in one way and the other one need not get compressed or expand. And when we go to a turbine, we see that if you have liquid droplets in a vapor, then the droplets, because of their own inertia, can move around, and they can really move very fast, and they can impinge on the surfaces, and they can create erosion of the surface of the vessel in which things are contained. So that's where the difficulty lies. So it's not just liquid or it's just vapor, it's just that when you have a combination, you have difficulty. Now, superheating I had explained last time, and therefore it turns out that Carnot cycle is very difficult to implement practically. So one essentially goes to the Rankine cycle and say that that is the ideal cycle on which we can design our power plants. Okay, any question thus far? Okay, so we looked at further that if we were to increase our, change our pressures. So let us say I want to get more work by reducing the exhaust pressure. So basically what we are doing is, in this line here, so you can think of that there are two pressure levels. One is this pressure level here, and the other one is this pressure level. So these two pressure levels would have, so one you can stop here, okay, or you can stop here, okay. So this is at one pressure level, this is another pressure level. Which one do you choose and why? So here you can see that if I'm at this pressure level, of course this is at a higher pressure level, not lower. Just that things are drawn here, and therefore I'm just using that. So if we were to stop here, then you can see that I'm closer to this point here. So my quality is expected to be larger. Whereas if I come here, then my quality is lower. And of course, if I take it further to at still lower pressure, then my quality would be still lower. So that's what has been stated here. So it implies a lower quality for the steam which is passing through the turbine. Although in terms of heat rejected, I may have to reject a lower amount of heat. So essentially you are looking at how much heat. So this is the part over which heat is getting rejected. So you have to look at this change in the enthalpies here, and you have to look at the change in enthalpies here. So typically it turns out that this would be, I mean, they would be reasonably comparable, although the figure, it is not that apparent. So you see that the amount of heat uh, which is rejected, and especially the temperature at which you are rejecting the heat, is now lower, and therefore the efficiency is expected to be slightly better off. But the fact that you have to deal with a lower quality mixture, that's where the difficulty lies. Now, the other thing that you could do is to see if you could raise the temperature further when you are adding heat. Why just stop at 3? Why not go into the superheated region? And this is something which is commonly done. And this is a very practical way of doing things, because it turns out that you add this extra amount of, so if you have to look at amount of heat which has been added, you can look at, again, if everything is reversible, then delta Q is equal to TdS. So essentially it becomes the area under this curve. So the heat which has been added is all the way from 2 to 3 prime, and the heat which is rejected is the area which is below this region. So the difference of these two, which is this region here, which is enclosed by this TdS, or by your cycle, is the work which has been done. So you can see that if I were to add this segment, then the work output is going to increase because I get this extra area. Now, if you want to look in terms of efficiency, then you have to think of, because you're also adding more amount of feed. So has my efficiency increased? So it becomes slightly more difficult to argue, but you can argue from the point of view of that my average temperature has increased. Average temperature at which heat is getting added is increased, and therefore I expect the efficiency to increase. So that's essentially, so you can see that superheating does this. It increases the average temperature, improves the overall efficiency of the cycle. It also helps to extract more work. And of course, it helps in the sense that the quality of the steam which is leaving the turbine is also larger now. Okay, you can see that, of course, everything has shifted towards the right, and therefore the quality is increased. So it seems to have lot of advantages here. And this is something which is commonly employed in practice, is that you don't terminate at 3, you go all the way to 3 prime. Of course, earlier we could locate this point 3 without any difficulty. Now you need some additional information to figure out where is this point 3 prime located. Okay, so I will have to give you the maximum temperature maybe of heating or something else, okay, to determine this point 3 prime. Otherwise, of course, 3 could be located, 3 prime cannot be unambiguously located unless and until there is something else, some other information which is given. Okay, any questions here? So now we can see what would happen if we were to increase the pressure. Maybe let me just try to illustrate it through here. So let us say that this is our pressure levels. This is how we are operating. So now what we want to do is look at a higher pressure. So maybe we want to go to this level. Okay, and on this side, we are going to move like this. Maybe use a different color. So what we would like to keep here constant is this temperature. So let us say that I am looking at this temperature constant. Of course, this is a TS diagram. So we want to hold the maximum temperature and the exhaust pressure constant. And would like to see how much work has been produced. So you can see that if I increase the pressure now, if I'm increasing the pressure, I'm keeping the maximum temperature constant. So I'm essentially maintaining this level to be constant. Okay, and of course I am at two different pressures. So I think, I don't know why I wrote exhaust pressure is constant. Okay, I don't think that can be correct. But maximum temperature I'm holding constant. Now the work produced, now what happens to my work produced? So you can see that the work produced is going to be, so I have to draw this line here. So essentially I'm looking at this area versus in the other case, the area that I was looking at was essentially this area. Okay, so these you have to look at the two areas. That is essentially the work which has been done. So it's difficult to say, and it turns out that the work produced may or may not increase. Okay, but one can look at amount of heat which is rejected. In this case, In the red case, this is the point. We go from this point to this point. In the blue case, we go from here to here. So it is clear that the heat rejected that I have to reject is going to reduce uh, in the blue case. So, so work has not changed. My heat rejection has reduced, and therefore my efficiency has increased. Okay. So this is the advantage that you see if you were to raise the pressure. But the only difficulty that you see now is that you are closer, or your exit of the turbine is at a lower quality, and you have the same sort of difficulty which I have not repeated. Okay, you have the same set of difficulty that you had seen earlier with respect to dealing with the low quality steam at the exit of or as it is passing through the turbine. Yes, no, why am I not hearing anything, or what is the problem?
No, sir, it's clear.
Okay, good.
Sir, how did we claim that temperature? Like, I didn't get how do we comment about the average temperature in all these cycles?
Average temperature we are getting because in this case, the heat addition is happening. Let me just use a different color. So maybe this is the point at which we start adding heat. We go here, we go here, and we go here. Okay, you can see what is the temperature that you are getting. So some sort of an average temperature between these 2 points would be here. It means, of course, here the temperature is constant, and here the average temperature would be somewhere here, right? So you can now take average overall, and you can say that wherever it lies. So that's essentially what we are doing. We are trying to get some sort of an average temperature over which the heat is getting added. So going all the way from here to here, or from here to here. Is it clear? Does it answer your question? Because I don't know how much you are seeing and how much of of course, my pen movements are not able to see, so I don't know how much you have understood.
But in this blue curve, which was for higher pressure, it seems like the um, terminal temperature is nearly equal to the um, terminal temperature for the red curve. So how did we get that temperatures is average temperature is changing for them?
Yeah, so what we are arguing in this case is we are looking at the work done. So the area which is enclosed by the curve, that is my work done. So I look at the two areas and I find them to be comparable. So I know that the work done is comparable, uh, but I'm rejecting lesser amount of heat because we are going from here to here versus here to here. So here we are looking at not temperature arguments. We are looking at the amount of heat and work amount of work which has been which has been done in the cycle, and the amount of heat which needs to be rejected in the cycle. So we are claiming that so we are looking at W upon QH actually. So of course you'll have to write it out in terms of my QL. So we are saying that the amount of heat which has been rejected is lower, but the work done is the same. So that means, of course, the amount of heat. So we are saying like efficiency is, of course, work done divided by my heat added, and then it is W upon QL plus W. So if we get W to be the same, so if W is the same, then of course if QL is larger, um, then my efficiency is lower. Okay, and we are saying that if you go from this cross to here, okay, you have one QL versus if you go from here to here, you have a different QL. And of course, for the circle, the QL is lower and therefore the efficiency is larger because the work done is approximately the same in two cases. That's the argument that we are making.
Okay, sir.
Sir, I'm still not able to like graphically understand why we would have a greater, like lower amount of heat rejection. I'm sorry, but can you go over that bit one last time, sir?
Yeah, so heat rejection. So we are essentially looking at this expression here. Efficiency is of course work done divided by QH, right? So this is like, so this is a straightforward expression. Whatever we have written here, this is straightforward. QH is equal to just QL plus W. Now we are looking at heat rejected. So heat rejected in this case would be this much. In the other case, it will be that other. So in this one case, it would be this much area. In the other case, it will be this area in addition. So of course, when you go from cross to cross, cross to cross, it will be larger. Is it clear or still not clear?
Oh, okay, sir. Yes, sir.
Yeah, I just prefer a blackboard here. This is just not convenient. Okay. So if you were to summarize what would happen, and of course this now answers the question that was asked to you a long time back about what you would do if you remember to increase the work output from a turbine. Okay, so at that time I had not given you the answer, so but now we have given you the answer. We had asked you to think about these possibilities and do some calculations. If you had done it at that time, hopefully whatever we are giving now without any calculations would be much easier to follow. So in summary, we have looked at three things. We have looked at the effect of pressure and temperature on the Rankine cycle efficiency. And we found that reducing the exhaust pressure or increasing the pressure are both beneficial for us in terms of increasing the efficiency. And similarly, increasing the temperature, which is by superheating the steam, is also helpful to us. Now, if the other thing that we started worrying about is the quality of steam, which is leaving the turbine. And we found that increasing uh, the quality of the steam which is leaving the turbine increases by superheating the steam, which is good for us. Whereas in the other two cases, it reduces. That is by changing the pressure, whether we are increasing the uh, pressure level at which the heat addition is happening or reducing the exhaust pressure. In both the cases, we are finding that the quality of the steam which is leaving the turbine is reducing, which is not something which is desirable. So that's the sort of bottom line that we get. And again, pause for any questions before we move ahead.
Sir, if we reduce the exhaust pressure, won't the average temperature at which heat is being added will also reduce?
Yeah, so we said that. I think this point is already there in the slide. So heat rejection reduces. Okay, that's already given to you. The same argument that was just given. Okay, and yeah, we are seeing the same thing that you are saying. In this sense, I'm missing
Okay,
something.
okay, yes, sir. I got confused because of the exhaust pressure.
Any other question?
Sir, if we increase the pressure at which heat is being added, we might also decrease the amount of heat added because all it is doing is reducing the heat that is rejected out of the system while we cannot say anything about the work.
No, I did not follow it. Can you just repeat your question?
So in the third case that you explained that we can increase the pressure at which heat is being added.
Correct.
Yeah, sir. So that might also lead to reduction of heat added because, sir, we cannot say anything about the work that is produced. But we can surely say that heat is rejected, that heat rejected is reduced. So how is that beneficial?
Okay, so I think we are already saying that uh, so we have sort of argued, no, I mean, from the figure also we could see that our areas are not changing too much. And yeah, I'm not sure if I understand your thing fully. So I think you are talking about the heat addition which is happening. That is lower now. And
Yes,
you
sir.
are saying heat addition, heat rejection is also lower.
Yes,
and
sir.
therefore I cannot say anything. I cannot claim anything. That's the statement you are making, right?
Yeah. Yeah, sir.
So yeah, the statement that we are making is that the work done, which is there. So we are looking at not from the point of view of heat added, we are looking at it from the point of view of work which is being done. So if you compare the two areas, the areas turning out to be reasonably similar. So that's how you can say that the work addition, the work which is being done in the two cycles is similar. And then, as you said, that the work and the heat rejection is definitely different or lower in one case, and which wherever it is lower, it is going to be the overall efficiency is going to be larger.
Okay, sir. All right.
So I think maybe you can just sit down and draw a little bit more carefully. This is too freehand and just not turning out well. I mean, I'm not happy with the figures, the quality of figure that we have here. Maybe a board will be much better. So you can draw it a little bit more carefully and you can see what is happening to the areas and you can see whether these arguments that we are making the slides are reasonable or not. Okay, any other comments or questions here? So basically what we have seen is Rankine cycle and some of the various common variations that can happen in there. So of course there are a lot of variations, further variations that one can bring about. So we will only talk about one interesting and an important one, and we will not bother about others. I'm sure when you go to the applied thermodynamics course, you will see much more of this. So this is like a precursor to a much more detailed analysis that you would be doing in that course. So let me maybe show you the figure here. And so this is an interesting way of doing things. So what you are doing here is going from 1 to 2 and then you have gone to 3. So this is as before, 1 to 2 and then going to 3 is as before. And then when you're expanding it, you go to the point 4, but then you do not continue expanding because we have seen that we don't like uh, low pressure, low quality steam in our turbine. Okay, so we don't like that. So what we can do is reheat this at this stage. So we are adding extra amount of heating, and of course, then we take it to another turbine, and then we complete the cycle. So you can see that we have avoided the point of low quality altogether in this case, and of course we have gotten some extra amount of work which is done here. Of course, comes with the cost, which is that we have added more heat. So any difficulty, any comment that you would like to see to make about this, because there are some interesting comments that one can make before we actually put our own comments. So idea hopefully is clear that why are we going with the lead? Is very clear.
Sir,
Reheat it again. Yeah.
if we name this point 7 as the last point for the steam,
Mhm.
then what is happening in 6 to 7?
So this is my point 7 you are saying. Is that what you are saying? Yeah, so this is
It's
still
not
a
showing in
heat
the slide.
rejection. Yeah, so if you're thinking about this point here, somewhere here, where my cursor is.
The one which would be in horizontally aligned with one at the steam side.
Okay, let me just. So we are going all the way to this point. This is my point. Why should you see if you want to come further down, then you are changing the pressure level. Okay, because then if you want to come to this point here, that's what you would, if you are thinking that, if you're coming to this point somewhere here, then this is going to be at a different pressure level. This is going to be at this pressure level. Okay, this is of course at a lower pressure. So from the here to here, I will have to go for a lower pressure. I will have to change the pressure as well. Okay, which is not something I would like to do. So now what we are talking about is um, So we are talking about this point, coming to this point. Okay, this is at a pressure level. Now, if you are thinking of coming to a lower pressure, you are saying that if I'm at the same line, horizontal line as point 1, so I'm essentially coming to this point in this case. Then I'm going to be at a lower pressure level, because then this is the pressure level that I'm now having. Okay, so then my condenser. So basically what we are doing is we are taking this steam in the condenser, we are rejecting heat, and we are changing the state of this steam from the state corresponding to this 0.6 to the 0.1.
Okay, so from 6 to 1, there is only heat rejection.
This is only heat rejection, correct?
The work from the turbine 1 is 3 to 4, and from the turbine 2 is 5 to 6. Am I correct?
Yeah, that's right. So this is turbine work 3 to 4, and 5 to 6 is also turbine work. Heating here is now from 2 to 3, and then again from 4 to 5.
Sir, why can't we take the point, like the line 5 to 6, like vertically below till it touches the dome, and then at that pressure take it back to the initial state?
So I think what you're thinking about is a vertical line here, correct? Is this what you're thinking, a vertical line?
No, so the vertical line 5, 6, and then taking that vertical line down till it reaches the dome.
Yeah, so that's what was asked earlier. So that's, then you are locating this 0.6, this point, this dot here. Let's see if you can see things as I'm drawing now. So if you look at the reheat, I come to this point, and then I heat again, and then I come to this point somewhere here. Okay, so this is what is happening. Now, what is the question now?
So my question was that we are meeting point 0.6, and then we are taking it along the isobaric line to the dome. But instead of that, if we take it vertically down, and then we can exhaust at a lower pressure, so that will improve our efficiency, right?
Yeah, so let me just tell you that this is only 5, 6. These are only like some schematically which has been drawn. Okay, so ideally what you would like to do is to take this 0.4 at saturated vapor, and again 6 at saturated vapor. You can do this. Of course, you can try to get more work by reducing the quality still further. So the way I have drawn it on the iPad is actually what you can. So you may want to take it little bit inside the dome, so that your quality is not 1 but slightly less than 1. Let us say 0.9. If you can tolerate 0.9 or 0.95, whatever you can tolerate, you can take it to that level, and then you can go for a heat rejection. Because if you are actually stopping here, if you are stopping somewhere here at a higher pressure line, then you are not extracting enough work. You have more work potential, but you are not extracting that. If you may be just going in this way here.
Yes, sir. That's just what I wanted to ask.
Yeah.
Okay, I got it.
So right now, this is just schematic. In the actual calculations, the figures, problems, you will see where this point 6 is located. So typically, you would like to locate this point slightly inside the dome. Okay, so what we see here with the Rankine cycle with the reheat, it avoids the problem of high moisture content in the low pressure turbine, and reheat cycle takes advantage of increased efficiency at higher pressure while avoiding problem of excess moisture. And the steam is expanded to some intermediate pressure and then reheated. And then this reheated steam is finally expanded in the turbine. And of course, the overall efficiency uh, can be improved and the problem of moisture can be avoided here. Of course, one can ask the question is, instead of reheating, if we had added the same amount of heat in this part of the cycle itself and then taken it back. So whatever heat has been added from 4 to 5, if that heat were added at 3 and continued with that to some other level, okay, and then brought it back, how would things change? So any guesses?
Sir, it might reach the melting point of turbine. It's a guess because the temperature would be very high.
Yeah, actually that's exactly right. Okay, so we actually limit this temperature T3 because we don't want it to become close to the melting point. In fact, all these modern turbines these days are actually operating very, very close to the melting point of the substance. So that is actually a very good guess. Okay, but from the thermodynamic point of view, what would happen? Which cycle would have a better efficiency, the reheat cycle or the original cycle, original Rankine cycle? Forget about the quality factor right now, the quality at which we are in. So let us say that is not a consideration. Then
So
which one will have better efficiency?
still the reheat would have better efficiency, I think, because we are adding heat at a lower average temperature. Like if we continue adding heat above 3, then we'll increase the average temperature at which we are adding heat, and that
Right.
will reduce our efficiency.
Why that should increase our efficiency? Why should that reduce our efficiency? Because my average temperature is now increasing, no? Average temperature at which heat is getting added, if that is increased, then my efficiency increases. The average
Okay, right.
temperature at
Yeah.
which heat is rejected, that should be reduced. So
Yes, sir.
essentially, you want
Sir.
infinity temperature and 0 Kelvin.
Yes,
You
sir.
want to
I
operate
said it
between
the other
infinity and
way. Yes.
0 and 0 Kelvin. Those are the two levels that you would like to operate at. So yes, so what you are saying is right. So if you could superheat the steam further, okay, which requires better material, as was pointed out, a simple Rankine cycle would actually be more efficient. Can you see the slides now?
Yes, sir.
Slides moving because again it is frozen. That's why I'm checking it back. Yeah, so this is the story of reheat. And so reheat is turning out, so reheat is done because of the material limitation. Okay, we cannot keep on increasing this temperature further, although it helps to increase our efficiency, but it is not necessarily possible to keep on increasing this temperature further and further. Okay, and we may want to go for a reheat, and this reheat does quite a good thing, good amount of things for us otherwise. Okay, so I think as promised, we'll stop here and we have the quiz.